Hello and welcome to our lesson on base 10 numbers. So if you didn't know already, the numbers that we use and work with every day, those are what we call base 10 numbers. We're going to call them base 10 numbers because every digit in the place value of one of our numbers represents a power of 10. So 10 is the base of our number. Every digit represents a power of that base, a power of 10. And those powers of 10 start at 0 and increase by 1 with each place value. So remember the place value chart when we reviewed the whole numbers. When we start with our place values, we start in the ones place. Well, that value 1, again, is a power of 10. It's 10 to the power of 0. And 10, the next place value, is the next power of 10, 10 to the first power. 100 would be the next power of 10. 10 squared makes 100. 1,000 would be 10 to the third power. And then we just keep increasing our power of 10 by 1 as we move along the digits or the positions in that place value. So we've got 10 to the 7th, 10 to the 8th, 10 to the 9th, 10 to the 10th, and then over here 10 to the 11th power. And those could just keep increasing, but these are the common ones that we encounter, okay? So let's try to unpack that a little bit by expanding a couple of numbers. So let's take, for example, number 1 here. If I was just reading this number, I would read this as 4,792. I'm going to write that out. So the name in words would be 4,792. And remember those two-digit numbers, like 92, we get the hyphen, and we're not saying the word and or writing the word and in these names. We'll encounter that later with decimals, but 4,792 is our number. And again, that 4,000, we're reading that way because 4 is in the thousandths place of that number. So that represents 4,000, right? Plus, we've got that 700. Again, we're calling that 700 because 7 is in the hundreds place. Plus, we've got the 90. And again, the 90 is in that tens place. It's a little less obvious because we're not reading the 10 there. But lastly, in this digit, we've got the 2, so we'd add 2 here. And we have now the written form of our number. We also have what we call the expanded form of our number. Now, I want to expand on the expanded form. There's a couple of other ways to write this expanded form. So when we say 4,000, or we say there's 4 in the thousands place, that literally means that we have 4 1,000ths, 4 1,000s in our number, or that could be written as 4 times 1,000. Plus the 700 means we have 7 hundreds. Plus the 90 means we have 9 tens. And then plus the 2 there means we have 2 in that ones place. Okay, now, again, just to take this a little further, there's another version of the expanded form that's writing these 1, 10, 100, 1,000, those as actual powers of 10. So when we say 4,000s, this is really 4 times, and we can use the x for multiplication or parentheses, either one of those. It's probably more commonly written with the times when we expand it out in the powers that we're going to see in this next step. So 1,000, again, the 1,000 in our thousands place here, that 1,000 is 10 to the third power. So we could also call this 4,000 or 4 times 1,000, 4 times 10 to the third power. Plus here, 700s, again, this is 7 times 10 to the second power. 10 to the second power makes 100. Or we could say here, this 9 times 10 is 9 times 10 to the first power. Plus on this last one, we have 2 times 1, and 1 is 10 to the power of 0. So these are all technically acceptable forms of our expanded, or acceptable expanded forms of our number. So these are all acceptable forms of the expansion. They're all considered expanded form. One of them is just in terms of the powers of 10, and this is probably the one that we're going to use the most moving forward just because we're going to be building off of the concept. But again, any one of these would be an acceptable expanded form. So I want to try to write that expanded form one more time with this next example. So in this next one, we have 1,056,328 for our number. I don't want to go through writing all of these out, but again, just so we can see the expanded form or the new version of the expanded form, that 1 is in the millions place, so it represents 1 million. And I'll write the commas here so I don't lose my zeros. And then we have 5 in the 10,000s place, so that's 5 or 50,000. Plus we have 6 in the thousands place, so 6,000. We have 3 in the hundreds place. We have 2 in the tens place, and then we have 8 in the ones place. So again, we could call this 1 times a million. Too many zeros. We could call this 5 times 10,000. We could call this 6 times 1,000. 3 times 100. And I'm going to have to scoot this over because I wrote entirely too big. We've got 2 in that tens place, and then lastly 8 in our ones place. And then to go that last version of our expanded form. Again, this 1 million is 10 to the 6th power. And if you're not wanting to reference your chart there, the number of zeros in your number here is the same as your power. So 1 million has 6 zeros, it's 10 to the 6th power. And then we have 5 times 10 to the 5th, plus we have, oh sorry, that's the 4th. We skipped a digit here, we had nothing in that 100,000s place. Plus we've got 6 times 10 to the 3rd, plus we have 3 times 10 to the 2nd, plus we have 2 times 10 to the 1st, and then lastly 8 times 10 to the power of 0. So again, every digit in that place value represents a power of 10. So we read this digit as 6, or the digit in this one, 6 in the thousands place, represents a power of 10. It's 6 times the power of 10, the third power of 10, so 10 to the third power. Okay, not saying that very well, but hopefully you get the idea. All right? So now that we've got that down, I want to talk about counting in Base 10, which obviously we know how to count in Base 10, but remember, we're going to be trying to teach this to new learners who haven't seen it before. So in a Base 10 system of numerals, again, this is just the system that we use every day, we're only using the digits from 0 to 9 to count. So when we are counting, we're only using the the digits from 0 to 9. They just recycle after we pass the number 9. So we got to remember that only one digit can be used in each position or place value. And that 9 is the largest digit that can be used in any position or place value before we have to carry over to the next one. So when we're counting, it's really just a process of adding 1. And I grayed out the first box here, although our list starts with the digit 0. When we count, we start counting at 1. So if I was just going to count the Base 10 numbers, and just humor me for a minute here, I know we know how to count, but we're going to go 1, then 2, then 3, 4, 5, 6, 7, 8, and 9. And what happens when we get to 9, again, when we're counting here, we're really just adding 1, right? 1 plus the 1 makes 2, plus 1 is 3, plus 1 is 4, and so on. When we add 1 to 9 to get to the next number, which we know is 10, what's happening? Well, what's happening, because I can only, well, 9 is the largest digit that can go in that place value, is When I add 1, I get to the next power of 10. So I'm no longer in that singles, in those ones, the 10 to the zeros, which are ones. I add 1 and I get to 10, which is the next power of 10. Every time I get to the next power of 10, I have to add a digit. So what happens is I'm going to add a digit to the next place value, which is the 1 in our number 10, and then we start over or reset the count on the singles. So now I go through my 1 digit, my 1 in the tens place, and again restart the count in the ones place. So I'm leaving the 1 in the tens place, and then it's one more single. So I'm going to continue to add 1 to that ones place every time I count. So I have 1 0, then 1 1, then 1 2 to make 12, 1 3 to make 13, 1 4 to make 14, 15, 16, 17, 18, again 19. When I add 1, again, adding 1 to this takes me to the next power of 10, so I have to add another digit into the next place value. So adding the 1 here is what takes me to the 20. So I've got 1 9, and then I add to my tens place and reset the count on my singles, my ones place. So then 21, 22, and keep going here. When you get to 29, again, add to the next place value, which makes that 3, reset the singles. 31, 32, 33, again to 39, add 1, which adds 1 to the tens place to make 4, and resets the count on the singles, okay? And then I'm going to forward here a little bit, fast forward, because I know you know how to count, but oops, after 50, then we do 60, 70, 80, 90, and then when we get all the way down here to 99, when we go to add 1 here, we know it's going to reset that and add 1 to the next place value, but that gives me 10 there. Again, every time I reach a power of 10, I got to carry or add a digit, carry over to the next place value. So that's going to reset there, and that's going to have to add a digit into the hundredths place. So we go from 99 to 100 because we've reached the next, sorry, that's supposed to be the 99. We go from the 99 to 100 because we had to carry over into that next position. And that's why when you get to 999, right, that sequence of carrying over happens. Every time you get to a power of 10, you have to add on a digit or carry over into that next place. Now again, this is something that we know how to do. We just sort of automatically do it. But it's an interesting concept to teach someone who has never seen the digits before, who has never counted before. So just to kind of give you a way to expand your thought on this, I want to show you again, expanding your thought, just a way to think about what is actually happening when we're counting. So let's suppose that you own a cupcake bakery and you have the following types of boxes to package the cupcakes that you're selling. So you've got this box called the cube, and it holds 1,000 cupcakes. You've got another box called the square, and it holds 100 cupcakes. You've got another box called the long box, and it holds 10 cupcakes. And then you've got this box called the single. It just holds one single cupcake. And you'll notice that we've got 10 to the 0, which is 1 here, 10 to the 1, which is 10, 10 squared, which is 100, and 10 cubed, which is 1,000. So these are just our powers of 10, like our places in our place value or positions in our place value, okay? So you're going to package the cupcakes that you sell into these boxes, but you got a few rules. You want to package efficiently, and these are the rules to help you do that. You always want to use the largest box that's possible for an order. You can use combinations of boxes, that's totally fine, but you don't want any empty spaces. So you don't want empty spaces in any box that you're using. That would be wasteful. So with those rules in mind, think about how you would package certain orders. If I said to package an order of 5 cupcakes, we're not going to put 5 cupcakes in a long box because you'd have 5 empty spaces there. And obviously you would have empty spaces if you're using anything larger. So the only option to use or to box these, to package these, would be to use 5 of the singles. So 5 cupcakes to package in that order would require 5 single boxes. Okay, if you wanted to package an order for 9 cupcakes, again, you're not going to go into the long box here that holds 10 because there would be one empty space. The only option would be to use 9 singles. 9 singles, and you'd be good. Now, as soon as you add one more cupcake to that order to go from 9 to 10, just adding one cupcake, you're no longer going to use singles. If you used 10 singles, it wouldn't be efficient because we do want to use the largest box that's possible. So as soon as we add one cupcake to that order, it takes us into the next size box. So if we wanted to do 10 cupcakes, well, now we're going to use one long box. Now, if you wanted, let's say, 14 cupcakes, you want to use the largest box possible. Well, there's space there to use one of these longs, so one long box would be used. That would fill, or 10 cupcakes would fill that, which means you have 4 left over. So this would use one long box and then 4 singles. Okay, and you kind of hopefully are seeing the idea, right? If you would 27 cupcakes, still not going here, but I could do 2 long boxes. 2 long boxes would take care of 20 of those cupcakes, and then the 7 singles would be left over to go in those single boxes. 4 single boxes. Oh, sorry, 7 single boxes. If I did 80 cupcakes, we're getting close to this, but still don't want to go there yet because there'd be 20 empty spaces. So that would be 8 of our long boxes, right? 8 long boxes here. 98 cupcakes, again, getting close but not quite there. I would have enough to do 9 of my long boxes, and that would take care of 90 of those cupcakes, which means the 8 left over would have to be packaged into the single boxes. And then I add 2 to that, I go up to 101. Well, now I've got 100, so now I can use one of those square boxes, but I'll have one single cupcake left over. So this 101 would use one square box to take care of the 100. We don't technically have to write it, but we're not using any long boxes, so 0 long boxes. And then, let me just check that out. We have one single left over. Okay, maybe it's important to note the 0 in the middle, but that's kind of what's happening, right? 980 cupcakes. So 980, again, not quite to our 1,000. We're going to have to use 9 of our squares to take care of the 900. We're going to have to use 8 of the long boxes to get the 80, and then no singles, right? And then finally this last one, 1,150 cupcakes. I've got 1,000, so I can use the largest box or the cube. So this would be 1 cube. And then I have 150 left after I take care of the 1,000. So in that 150, I could definitely get a square, right? I can get 100 out of there. So 1 square. And now I've got 50 left. Well, I can take care of those with the 5 long. And then 0 singles. Okay, so that's kind of the idea. Think about packaging numbers or grouping numbers together. When you're in the singles, right, you're not going to jump over to the next group until you get to that power of 10. Or you can't go to the next group, right, until you get to that power of 10. So hopefully that idea of packaging the cupcakes gives you an idea of how to think about or approach the concept of counting with base 10. It's definitely something that helped me when I was trying to help younger learners understand the concept, and I think it'll really help when we further this and start looking at numbers in other bases. But for now, I think that's a good place for us to stop, so give your homework a shot, and if you have any questions, by all means reach out. Until next time, take care.